speaker is from John Hopkins Applied Physics Lab, Abigail Reimer, and she's the principal investigator on this Neptune Odyssey, got her degree back in the United Kingdom. So please welcome me as we listen to the Neptune Odyssey NASA mission to the Neptune Triton system. Welcome.
Thank you. Thanks, Nick, and thanks for thinking of getting me involved with this. This is a really nice group to be talking to, and yeah, do keep me posted on your work going forward. It's very interesting. And also remind me to send you the slides so you can quickly look through them if you want to refresh your memory. All right, so yeah, so we had, there was about 10 studies selected for the planetary mission concept studies. Not all of them flagship class, but all of them either New Frontiers or flagship. So that's a $1 billion mission to a mission with no formal cost cap, a flagship, but normally you're looking at something like 5 billion to be Cassini class mission. We actually landed at 3.5 billion, so that was, we were pleased with that. Right, so I was ably assisted by an early career scientist who is my project scientist, Kirby Runyon, who's also applying to be an astronaut, a very cool guy. And our lead system engineer is an engineer at APL with an enormous amount of experience in mission design with Brenda Clyde. We had a very large science team as befits a mission of this scale. I think we had about 50 co-Is and an article which is preparing for the PSG Planetary Science Journal. We have 72 co-authors, including the engineers. So that was fun, submitting that journal article where they make you put in every single author's name and address separately. It took me longer to do that than it did to write a paper. So we started with very deliberately with a distributed leadership structure. So this is something that I put up front because it's something I'm particularly proud of, and I think that it's a really excellent framework for future studies, and it's built on experience that I've had, but also for working with sociologists on the Cassini mission and now on the Europa Clipper mission in particular. Janet Battisti at Princeton, who's actually got a book coming out soon comparing the Mars mission and the Cassini mission. So, and I gather maybe even some gossip about those missions to be had in that presentation. I'm just moving the chat in case I need to read it. So yeah, we went with the unabashedly flagship class mission, and I think that was really our win theme. So for the PMCS proposal round, it was very competitive, and I know of 6 ice giant related missions that were proposed, and there were possibly more. So this was the only one that was funded. So because obviously ice giant missions have been studied very comprehensively in the past, and there's been quite recently a JPL study was 2017 led by one of our co-Is, Mark Hofstadter, that describes Uranus and Neptune missions that can be done for on the order of 2 billion. So we were looking at both the unabashedly flagship class, but also bringing very deliberately the Triton moon element into the study, which hadn't been looked at in great detail as part of the previous studies. And that was partly because Triton has been recently looked at again in the context of perhaps being an ocean world and looking for ocean worlds. We've kind of looked for follow the water as the outer planets community as being the places to look for life, and as we've sort of done on Mars as well. But there's the hope that there's existing water on places like Europa and Enceladus, and reanalysis of some of the data from Triton has led us to wonder if some of the plume activity observed by the Voyager 2 during its flyby was perhaps not due to just sublimation due to solar effects, which is what we've kind of assumed, but maybe evidence of subsurface water. So really exciting and vital to go back, and also to leverage the sort of excitement that we got from the Pluto flyby. So we organized ourselves into working groups, most of them familiar for something like an ice giant mission: Aurora, Magnetosphere, satellites and rings, Neptune. We also had a working group specifically looking at what sort of observations we need to make in order to place Neptune and or Uranus in appropriate exoplanet context. So what do the astronomers need in order to understand their observations of the super Earths or the mini Neptunes that are increasingly large part of the family of exoplanets that are being increasingly discovered, and especially in preparation for the James Webb coming in the next decade, hopefully. But then we also had the Triton working group. So we had very comprehensive, very much like Clipper's going to do for Europa. Triton flybys organized so that they are at different latitudes, so that we can look at the magnetic field as a function of Triton's longitude around Neptune. So then as the magnetic field rocks backwards and forwards, and I'll talk about this a little bit more later, but as the magnetic field rocks backwards and forwards across Triton, it induces a magnetic current in any salty subsurface liquid. And so that's how you discovered the oceans at Europa. And that's how we would discover if there was, or confirm or deny if there was any subsurface ocean at Triton. So that's the most important thing to do and to organize with the tour. The second thing that we wanted to do was explore a landed element. And that was really cool. So when we had our proposal reviewed, our only minor weakness was that we hadn't considered a Triton landed element. And I'd made a deliberate decision not to, because I thought it was a bit too sci-fi for a mission of exploration. So them saying that that was a weakness kind of gave us the red light, the green light to go forward and look at a Triton landed element. And my favorite, and one that was received well by Planetary Protection, was the idea of an L-cross lander, so a ballistic impactor. So no science instruments on the impactor, but it would hit the surface of Triton, loft a plume that then the spacecraft could fly through. And I'm not going to talk about that more in this presentation, because in the end we didn't put that into the final proposal document. But there, I think there's talks recorded online that you can, or you will be able to access quite soon. We're documenting all of the process we went through to get to our final presentation. But the main reason is that one of the things one of my co-authors said, which I quite like, is that Triton has an atmosphere that's not thick enough to be useful, but not thick enough to be useful, so it can't do like a Huygens lander like we do at Titan, but it's thin enough to be dangerous. And the idea, and it's a really large moon, so the idea that the plume would loft to an altitude that it could be measured by a spacecraft that was flying past it safely was very much not clear. So we hated the idea that we might carry this brick all the way to Triton, drop it on Triton, and then not actually be able to safely get close enough to measure the debris. So that was the simple reason that in the end we didn't propose it. But we went forward, and we pulled on the thread to the extent that we realized that as a trade study, it was much more sensible to add even more capable instrumentation to the orbiter, which we did. And you'll see it's a very well-equipped spacecraft. Right. So the background of the Ice Giant mission is it's been supported in the Planetary Decadal Survey. It was the next priority down below the Mars Sample Return and Europa Clipper, so both of which are happening. So the next one down is the Ice Giant. So really we've been pushing for NASA to stand up this mission now. They don't need to wait for the next Planetary Decadal Survey, but we're hoping that the Planetary Decadal Survey, which is underway now with our beautiful proposal concept study in their grubby little forms right now, we're hoping that this is going to be the #1 target for a new star in the next decade. And it doesn't work like that. The fact that we were #3 behind 2 missions that are already happening doesn't automatically elevate you to #1. But I think that the addition of Triton perhaps being an ocean world, the great appetite in the community to get back to a Pluto-like world and to study Triton, which is actually slightly larger than Pluto in an orbit around Neptune, is really the only way we're going to do that in any time soon. And I'll note in the last decadal survey called Visions of Voyagers, they supported Uranus specifically. But what they said in the text is that Uranus is preferred because of the difficult requirements of achieving Neptune orbit. Well, that changes. And in fact, if we can launch by 2031, we can get to Neptune in almost in the same amount of time as we could get to Uranus. It's about a 12-year cruise to both, because of the orientation of Neptune with respect to Jupiter. We actually proposed direct to Neptune options, which is a 16-year cruise. And that's one of the reasons that we focus a lot on the cross-disciplinary elements of such a mission. So I'm hoping that during the 16-year cruise phase, we would make heliophysics observations in the solar wind. And it's a bit Pollyanna, but I think that I always look for the crossovers in science, and increasingly look for the crossovers outside of science. And I do think, and you'll see, like if you look at the history of exploration on the Earth, it's relatively rare that there isn't a poet involved or some artist. I mean, Berkman took a writer with him, and Shackleton had a poet with them on that mission to the Antarctic. So the idea that perhaps we would give over some of the crews to humanities, for them to talk about the history of what's been learned through exploration and use their imagination to come up with, I don't know what they would, because that's not my expertise. So I think one of the key things in the success of such a mission is to make sense of that cruise phase, if it is going to be 16 years. What I'd really love is for NASA to get their act together and have it ready to launch by 2031, so it's still a very long cruise. Not only that it would be a shorter cruise phase, it also means that you could simplify the mission and/or you could take a lot more mass. You could even add a whole other atmospheric probe. So I've already talked about that. So the first and only so far visit by humanity to Neptune was the Voyager 2 spacecraft in 1989. So there's a few figures here that I'll just talk about. So Neptune's just beautiful, a beautiful rich blue color. Its relatively quiescent surface has been observed several times by HST. This image was actually taken by Voyager during its flyby. The interesting thing that got me interested, and actually I used to be a proponent for the Uranus mission, and I still am. I'm not really, Neptune over Uranus. It's just that I'm particularly interested in having the different elements of physics work together. And so that's why Neptune just kind of trumps Uranus a little bit by having the Triton. It's also got one of the youngest, probably the youngest ring system of any of the planets in our solar system, and that's because of Triton. So you could think of Neptune as being a kind of a pristine ice giant as compared to Uranus, which we think has had a tumultuous past that knocked it on its axis such that it's actually rotating in the opposite direction of all the other planets in our solar system. So obviously it's had something tumultuous has happened to it in its formation. So therefore, it's probably not an example of a completely pristine ice giant world, whereas Neptune possibly is, or more likely is. Maybe neither of them are, but it might be our best shot in our solar system. On the other hand, Uranus has probably the most pristine example of an ice giant ring system, and they are weird moons. They're completely dark versus the moons of the other giant planets, Jupiter and Saturn, which are almost completely white. Like Enceladus is properly snowball white. They're very dark, and Carl Sagan was a co-author on a paper where he talks about it perhaps being due to radiation darkening. So that's something else to know about these planets. Uranus had the strongest radiation belts ever observed in the sense that they extended to the highest energy, not like the highest flux, like Jupiter has the highest flux, but they extended to the highest energies of any radiation belt ever observed. And then Neptune had the lowest, had virtually no activity in the magnetosphere and very weak and quiescent radiation belts. And I think probably correct, people like to say, oh, we can't possibly understand it, it's all so complicated. But I actually think it can be quite easily understood, and there's work by my colleague Carol Patty that shows during the season that Voyager flew past Uranus and Neptune, Uranus was oriented such that it would have had it's not rotating so that the magnetic field is open to the solar wind on every Uranus day, whereas Neptune was. So basically Neptune's open field lines rotated to be directly pointing at the sun at least once every Neptune day, which is roughly once every 10 hours. And what that means is that the solar wind had easy access to the Neptune magnetosphere, and so it can strip. It takes a while for radiation belts to build up, so it's stripping away the buildup of the radiation belts once every 10 hours. And so it makes sense that they would have had quiescent radiation belts. And by extension, if we go and visit Neptune at a different season, then most likely it will have equally strong radiation belts to Uranus. So anyone who tells you it's really complicated, it's not, I don't think. But we do need to go there, and highlighting the fact that that's one of the things you simply can't prove from a single flyby. You need to be able to sit and stare to be able to assess what is a seasonal effect versus what is a, what God sees, always true kind of an effect. So this image down here was also taken by the Voyager during the flyby. This is Triton, and the plumes, you see these grey smears down the bottom. This is the evidence of old plume activity. And I don't think it's easy to see on many of these plots, but papers written by Candy Hansen at the time show that the plumes loft to, I think it's up to 8 kilometers. I'm not sure that. Amazing storms in Neptune's atmosphere, and that was also a very interesting one. Was there was a poster at AGU years ago, Heidi Hamill told me about, and she's looking at a picture of Neptune, because Neptune had like hardly any clouds or anything like that, and she said, "What is that?" It's always a picture of Neptune. He'd just taken a picture and just thought, "Oh, that's a nice picture of Neptune," without really thinking about what it showed, and it showed the first observations of a storm on Neptune. So those kind of slowly we've been looking back and seeing if we could tell the difference between storms on Neptune and perhaps aurora. Again, with the magnetic field being at this strange orientation, aurora is going to happen at weird latitudes. So perhaps some of the things we've seen that we think are clouds are actually aurora, and that's one of the things I'm particularly interested in understanding. And it's a massive, really powerful diagnostic for knowing what's the nature of the internal of the planet, because if you can see aurora, and I think that that's something we can hope to be able to do in the near, and not too much. In fact, they've already got an observation of aurora on an exoplanet. But once we start making systematic observations of aurora on exoplanets, we can start to map their magnetic field lines, and that starts to tell us something about what's going on in the interior. So it's going to be a really powerful diagnostic, which again, we can test at the ice giants. And we can only test it at the ice giants by really going there. They really are just too far away for us to make observations of their aurora the way we can for example, Jupiter from the Earth. But also, of course, crucially, you only get that one view. And it's very challenging, even with the fantastic optics that we have now, to see Jupiter's full aurora in the way that, for example, the Juno spacecraft is making fabulous observations of in situ. So Voyager passed Triton at a relatively close distance for a flyby. I bet that was a stressful time for the Voyager scientists. I tell you, I would give a limb to have been a scientist, a young scientist in the era of the Voyagers. Must have just been the most amazing thing to have been doing. So they discovered a moon unlike any others in the solar system. So the sparsely cratered surface, and I'd just like to highlight again, this is where they see the plume activity in this sparsely cratered surface here, but here's what they call it, cantaloupe terrain. And they also see the equivalent on Pluto, but two completely different terrains. And I wanted to mention it because it's an extreme southern spring at the time of the Voyager flyby. The areas that they see the plume activity are going to be in darkness by some year that will be hopefully that is after our mission. So it's something like in the 2040s. So it's another reason that we'd like to go there soon. It's like a multi-decade season. It'd be nice to be able to go back and image the areas of the Triton surface that Voyager saw to see those seasonal changes. So I talked already about the plumes and the question of whether they are driven by solar energy. So that was the assumption for decades, was that it was sublimation just due to solar activity. But now it's now the question is it actually, are they being sourced from a subsurface ocean? The way that Enceladus are, the way that Europa plumes are. We actually don't have any examples of plumes lofting to 8 kilometers that aren't associated now with subsurface oceans. So what a fascinating situation to find a moon that's so far in the distant solar system that perhaps has liquid water beneath the surface, and perhaps liquid due to some amount of ammonia, which is the antifreeze that we think is enables a moon like Enceladus to have a liquid ocean, despite the fact it's so frigidly cold. So Triton, you probably know, but it's a Kuiper belt dwarf planet that was captured into Neptune orbit. So it orbits in a retrograde sense. So that was one of the things that's a challenge when we do the mission design. We're actually going to orbit our mission design. You really can do it either way, but we're going to orbit in the same, we're going to make a retrograde orbit at Neptune so that we're orbiting in the same sense as Triton. It's also very far off the equatorial plane, which is a shame because it'd be nice to stay in the equatorial plane at least for a little while to see the small moons that do exist, that did survive the arrival of Triton. But actually, in order to use Triton as a crank, we go in relatively equatorially, but then almost immediately we do a Triton flyby and then we crank so that we're in the plane of Triton. So one of the things that I wanted to do as part of the mission plan was to have some time spent in the equatorial plane. What we could do if we had a bit more money, and I think that the mission, if it's ever stood up in its reality, is that we'll have a mission that does flybys of Triton in this plane. Our current mission design then pivots to do very close inside the rings, close over the poles, to do radiation belt type studies. So I think that we could pivot between those two. We could do a more equatorial orbit before we go into the final. It'll be the same as the Cassini finale. We'll go into a high latitude right over the poles before we actually do a great plunge into Neptune itself. So there's a few tweaks, and that's really it wasn't money so much as time. It just takes a really long time to make all of those trajectory file to process. I honestly don't know how to do it. It's like magic to me. And if I was doing my career again, that may well be what I would go into. I think it's absolutely fascinating, the amount of knobs that they have to turn to get a full tour that closes. And ours is the first mission concept study that's actually provided a full tour that actually closes from launch to doing all the science that we want to do to end of mission. Every element is consistent with itself. And I honestly didn't appreciate quite how difficult it was to achieve that. So if we'd had a few more months, we could have probably done a few more tweaks, but a tweak wasn't like, hey, could you just make sure we fly past Triton on the night side a couple of times? And then it would be like a week later and say, okay, done. Okay. That's not the kind of, that's what I mean when I say tweak normally. So here's some close-up views of Triton. I'm going to move on to this. So I want to highlight in particular these papers by Paul Schenk and Francis Nimmo, were the ones that first talked about. So you can see really just in the last few years, scientists are starting to recognize that there are mechanisms that could provide the energy needed to explain really, the surface being as lacking in craters as it already was. It's interesting that we were trying as a community trying to explain that without ever thinking perhaps subsurface ocean, but these two papers were really the seminal papers where we started to go back and think, now knowing what we know now from Enceladus, it's I think if you ask these authors, they would say it's improbable that you would get such a young looking surface, evidence of plume activity, and for it not to be associated with subsurface liquid. And then it's the question of whether it's a global ocean. So remember how very different the south was to the cantaloupe smooth terrain, which is the bit that might be in the darkness quite soon. So why perhaps it's a puddle. Perhaps it's a puddle that's centered at the South Pole, a bit like the Enceladus tiger stripes are centered at one of the poles. So I talked already about the fact that the Neptune's moons were normal before Triton came crashing, and so Triton came in, disrupted what was probably a nice pristine ice giant moon and ring system, and caused it all to have to reorganize itself. And so it's a nice way to study a evolving ring system, which I encourage you to look particularly at that part of the report, which was led by that working group was Tracy Becker and Matt Hedman. And it gave me such a renewed understanding of, and having worked on Saturn for most of my career, I know a bit about rings. It gave me really renewed understanding about what a powerful diagnostic they are for planetary formation. So it's, very, very interesting and actually very cool to work with ring scientists who obviously have had a wealth of data at Saturn, who would really, if they have their choice, this is where they want to go, because it's the way to see ring formation and really planetary formation in situ. It's the youngest laboratory for that we have in our solar system. So there's a bit more about the ring system here, which I'm not going to read through. I love this movie was put together by one of our colleagues on the study, who I think it was Corey Cochrane, or he maybe extended the development of this model. So this shows you Neptune rotating in the solar wind. So you can see the sun, if the sun's solar wind is coming in from the left-hand side, now we have closed field lines. And there you go, now it's rotating so that it's open to the solar wind. Now it's rotating so it's closed to the solar wind again. And this is the sort of orientation that Neptune was in during the Voyager flyby. What it also saw, so I mentioned that it had the quietest radiation belts and the lowest energy radiation belts of any planet in the solar system. So that's this plot here from work by Barry Moak and Nikki Fox. And Barry's gone on to write several papers on this topic, doing comparative radiation belt studies, which is very interesting, and I very much encourage you to go and have a look at that. He writes in in really good plain English about what is, you know, famously a relatively complicated topic, but also a bit like the magnetic fields and the rings. You don't have to understand the microphysics of radiation belts to be able to grasp how powerful a diagnostic they are for planetary formation, and in particular the sources and losses of plasma in the magnetosphere, which is something that was really, really important at Saturn and Jupiter. So just running through again. So Triton is in retrograde orbit about 60 degrees to the equator, and it's spewing out this gas from these geysers. So we thought when we got to Saturn that we were going to find that Saturn's entire magnetosphere was full of particles from Triton. It's got the densest moon, it's got the densest atmosphere of any object in our solar system, so that makes sense, right? But in fact, when we got there, we found that the entire Saturn's magnetosphere was populated by water group particles, and Titan's mostly nitrogen and methane, water group particles coming from Enceladus. So so most of what you see in the radiation belts at Neptune isn't going to be sourced from Neptune. It's going to be sourced from things like the Triton geyser activity, although Triton's almost as far out as Titan was at Saturn. So we just don't know. That's the fact of it. We just don't know what's going to be the most significant source of plasma to Neptune's magnetosphere. And at the time that the Voyager was doing its flyby, perhaps the biggest source of plasma in the magnetosphere would have been the solar wind, because the solar wind had direct access about once every 10 hours. And what we saw was that the edge of the radiation belts, this is a plot against time. If you replot that against distance, the edge of the radiation belts is constrained roughly by Triton's orbit. So some sort of loss mechanism associated with when the radiation belts are trying to extend past the Triton orbit, that perhaps it suggests that there's a Triton torus, like we get the Io torus at Jupiter that perhaps hasn't been observed. Well, the Io torus at Jupiter in a Keplerian orbit in the equatorial plane, that's a piece of cake to maintain. But if you're looking to maintain a torus that's off equatorial, all of the Keplerian physics is going to try and move it down onto the equatorial plane. Is that true? Actually, that might not be true, because it doesn't know about how Neptune rotates. I take that back. So there might be a torus that exists at 60 degrees to Neptune's geographical spin axis. We just don't know. And I shouldn't talk off the cuff about to speculate on what the nature of it would be. But something that we haven't had a chance to observe, and Voyager probably didn't fly so close to Neptune that it could encounter any debris disks or anything like that. So one of the main topics of our proposal work was also how to understand the origin and structure of Neptune itself. So this is a very nice paper by Schubert and Sutherland in 2011. They're building off an older model to show all the magnetic fields of different planets, and this is the one for Neptune. So green is an inwardly directed magnetic field and purple is outward. If you saw this for Jupiter, Saturn, or the Earth, it would be just green on the bottom and purple at the top, which is what you get for just a dipole field. So, consistent with that crazy wire model that we were just looking at, this is the structure implied for the internal magnetic field, and the mystery of how that comes about is, we hope, something that we're just about ready to start to study with an orbiting spacecraft. I'm also a member of the Juno team, so I do have my optimism is contained in a robust fence of reality, and I know that we're struggling to understand the nature of Jupiter's magnetic field, and we are not quite left with more questions than answers, but you can see it from here. So the idea that it's maybe a mushy core and things like that are starting to have to be explored, because we can't explain the profiles that are being derived from the instrumentation on Juno. So the one thing that we're going to do to improve over Juno, and one of the things that motivated the Juno mission, was we're going to have an atmospheric probe. So Galileo had the atmospheric probe, which actually made amazing observations at Jupiter. Until I started really looking into an atmospheric probe, the one thing I thought I knew about them was that they were really unreliable. And if you go in and you get a single point measurement, such as I know this is a little bit of knowledge is a dangerous thing. The one thing I thought I knew about the Galileo probe data was that it went into a particularly arid area of Jupiter's atmosphere. But they don't really understand that, but they just had to, they speculated that that was the case because of the absence of water-free particles at the place it went in. So that gave me enormous pause of, do we want to put an atmospheric probe? What is the benefit of a single point measurement for all of the money and the complexity that introduces to the mission? Do we really want one? So previous to this, there's been a lot of people, there's been a meeting recently in France, in Marseille. The Europeans are very interested in participating in a mission like this by providing a probe, which would be brilliant because we're definitely short of money for such a mission. So that was part of the reason. There was that pragmatic reason that I initially just said, okay, atmospheric probe, go, because I'd like to have somebody else pay for it and I'd like to have as many people on our team as possible. But then as I got more into it, I realized that there are things like the noble gas ratios that there's no way to measure, make any inference from without actually going there. I mean, that's the reason they're a noble gas, they don't interact with anything. So you have to go there and you have to measure them. And if we didn't have those measurements for Jupiter, we wouldn't know half as much as we do. So it's kind of vital to at least send that one litmus test in. So if you're sending that one litmus test in, well, then you might as well send in a whole bunch of other instruments along with it. And I hope that you'll be persuaded by reading the rest of the report that the atmospheric probe is worth its weight in gold. To the extent that, you know, you might want to put a second one on that you could drop later on in the mission. And given that we came in at 3.5 billion, I think it's one of the things that if I was going to go back and do this again, I might just start with 2, because I still agree with my former self that a single point probe measurement is a little bit of information could be a dangerous thing. So just this is a plot of the exoplanets that have been discovered as of whenever this plot was made by Kepler and others. The orbital periods versus size relative to the Earth, and so this is Neptune's are along this axis. Until fairly recently, Neptune-class planets were the most common. So I quite like saying that in my motivating talks, but now the super Earths, as you can see here, are clearly the dominant class of planet discovered, and it's really down to what we're capable of measuring. I'm sure once we get capable of measuring Earth-sized planets and below, this is going to massively change, and we'll probably find there's an infinite number of planets of all sizes. So whether or not an ice giant is a true archetype of an exoplanet is something that we don't know. But of the 8 or 9 planets available to us in our solar system, though these are the 2, this is the one class of planet that we haven't got comprehensive data about. And so I hope that the Astrophysics Decadal survey, which they recently published, and I haven't had a chance to look at, but I wrote a white paper, and I think others did too, requesting that they specifically call out the desire for an ice giant mission by the astrophysics community. Even if they didn't actually give us money, they could just at least give us support. But it is difficult to ascertain what measurements they want. When I say they, the exoplanet community, what measurements should we be making from an orbiter spacecraft that is a direct benefit to the astronomers? And I did have an exoplanet expert leading the working group, Jonathan Fortney, and a lot of the time we came round to the realization that the way astronomers do it is statistical. So they build up an enormous number of observations of these planets. So having our one extra case was just another number in the statistics, and it was difficult to see what measurements we should be making that were going to be really directly relevant to them. But then I think that perhaps that's because we haven't done it yet, and I think that and also they're not observing the aurora yet. I think the minute they start observing aurora on exoplanets, then the sort of models that we produce, well, certainly we produce as a matter of course for the Earth, and we're only recently now starting to apply to the outer planets, will start to become incredibly important for exoplanet observations. You should get a wiggle on. Being typically verbose. That's my tendency, is never use a few words when a million will do. All right, so I'll talk about the mission and the payload, and then wrap up. So we named our mission Odyssey, One of the things they said is you can guarantee that the final mission won't be called Odyssey if you name it Odyssey in the first place. But I also know from having been on numerous teams that having a name and a logo and a pin, they even made pins. I didn't realize I had a bit of a problem with scale. Got your cameras on. Actually had a pin made. It says Sciencing during lockdown 2020. I didn't realize it was going to be so small. It's internet for you. As I mentioned earlier, we would like to have this mission stood up as soon as possible so that we can launch by 2031 and take advantage of a Jupiter flyby. But I decided early on that if I was sat on the Decadal survey having to decide, between these missions, and if I had one that said we have to launch by 2031 and NASA being NASA, I'd probably say, well, that's out. Because the one thing you know about NASA is you get launch delays, and if it hasn't even stood up yet, then it's 2020. Plus everything else we've got going on now. The idea that you would have it ready to go in 2031, it's reasonable to me, but it's probably too much of a constraint to say this is where we're going to put all of our eggs. So I made a decision, I think it was the right thing to do, to provide a mission scenario that's direct to Neptune. So using our big rockets, using the SLS with a Centaur upper stage, we could also do the same mission with a Falcon Heavy expendable. So that's not the Falcon Heavy that lands back down on the planet, but there's another version of the Falcon Heavy which has a greater launch capability because it's not carrying the extra fuel that it needs to land back on the Earth. So that with it would have to redesign the fairing a little bit, which is why we didn't choose that as our launch vehicle. But just know this, if anyone says to you, this mission can't go without SLS, this mission could go with one of the private launch vehicles, in particular the Falcon Heavy expendable. And I almost regret I didn't go with that one. We were very, very close at the start between SLS and the expendable, but things change quickly in space research sometimes. And that was one that at the start of this conversation, the SLS seemed to be the obvious choice for the Clipper launch, Europa Clipper. So we were like, well, that's great. They'll already have experience of launching Clipper. And now, hopefully Clipper's going to launch, but I don't think it's going to be launching on an SLS. So here's our spacecraft design. It'll be familiar to any of you who've worked on the Cassini mission in particular. We went with a particularly large high gain antenna, which enabled us to minimize the amount of fuel required. So that was our biggest constraint. Our two biggest constraints was the price, was the choice of trajectory. So that was a trade that we made, and we decided to go with these direct to Neptune things. The next one was the number of next generation RTGs, which are the green things you see on the bottom. We started off with 4, which is why they're not symmetrical. So now we have 3, so we're very happy about that. And then we had already put the rockets, the little thrusters on, which are symmetrical, and then it was difficult to reposition the RTGs, which is fine. It just means you have to be 3-axis stabilized during the tour. And a lot of just mission design is so fascinating. You save a little bit of money if you're spinning during the cruise phase. You can go into a hibernation. But when you actually do the maths on it, and remember that I'm quite keen to have us doing science or doing something meaningful with the time that we're spending in outer space with this mission. So I quite like to have an active cruise phase anyway. But when we dug into it, you save 160 million, which in the context of a 350 billion mission, isn't that great on putting it into hibernation during the cruise phase. So I'd also like that to be something you take away with you, is there's a lot of wasted opportunities for the sake of really a few of NASA dollars to keep a spacecraft awake during the cruise phase. And my experience in particular, as I started working on Cassini in 1999, just after the Earth flyby, because I was in the UK, and the UK funded people to work on Cassini during the cruise phase. So my PhD is on the solar wind, it's on interplanetary shocks, it's on the Jupiter flyby. I started my first chapters on the Earth flyby, and as a bit of a tree hugger, the one thing you could find if you Googled Cassini in 1999, because it had just done the Earth flyby and it's a nuclear-powered spacecraft, was "Stop Cassini now." And all my hippie friends are going, "What are you doing, Ryan? We're working on this evil mission." And but but it was 700 miles, 700 kilometers. It was a very close flyby, but really with very little nuclear material on board. Where was it? Yeah, so that's one of the biggest required enablers for this mission. I'll show you in a minute, but that's put us in a bit of an unfortunate situation with the current Discovery mission choices that are out there. So here's an earlier version of our spacecraft where we had the probe was actually on the top, and you see at this point we had the 4 RTGs. Here's our high gain antenna on the side, and this is us inside this is the diameter of it, and this is us inside the SLS Block 1B fairing. As you can see, we could rattle around in there quite happily. The Falcon Heavy fairing isn't big enough, but apparently for a mission of this size, they would redesign. It's quite common to redesign the fairing. It's not that big of a deal. So that's what we'd have done for the Falcon Heavy launch option. Here's a CAD drawing of the Odyssey spacecraft as it finally landed. We had a few changes in that. This is our microwave radiometer. It started off being 2 or 3. I think there's another panel on the other side, multiple panels, and we came up quickly with a nested design, which is one of the few tech developments, but it's really trivial. Mostly we were very, very conservative. All of the instruments have got heritage, mostly a lot of them from New Horizons, a lot from Cassini. So here's a list of the instruments on the orbiter. So we've got visible and UV and infrared imaging capability. Then we have, going into the further infrared and into radio wave, we have the radio plasma wave antennas. That's 3 10-meter antennas. And this is just the units as they would be mounted on the side of the spacecraft. Then a very comprehensive fields and particles suite that's based on the Juno thermal plasma, which is also in itself quite closely related to the Cassini thermal plasma observations. Energetic particles, again, similar to, this is one that's currently flying on Parker Solar Probe, and an ENA imager. So an ENA imager was flown for the first time, I think, on Cassini, which is quite crazy to think that it was the first time a dedicated ENA imager was flown was on an outer planets mission rather than an Earth-based mission. So it's been flown quite commonly since. And this is one of the rather sad but inevitable consequences of that hibernated cruise phase, was that we weren't making observations at the edge of the solar system when we could have been. The Mimi Inca camera on Cassini made amazing observations of the ENA emission from the edge of our astrosphere, so the edge of the solar wind at like a 1,000 AU, 100 AU, many AU. And we didn't start doing that until after the Jupiter flyby. So we missed out on 5 years of data that we would have been gathering, and you know, we argue to this day about the variability of that region of the edge of our solar system. So even 6 months of an extra data point would have been quite priceless, and would have been worth maybe not a flagship, but a New Frontiers level mission in its own right, as we know from what was soon after Cassini was the IBEX mission was selected to do exactly that. So the probe instruments, these are just cartoon drawings of the instruments on the probe and the spacecraft. And I'm not really that familiar with how most of the probe instruments work, but they have been studied to death. And we had Kunio Sayanagi, who was mostly coordinating the science from the probe. And I encourage you also to look up his work on that. He's been involved with small probe development and the science that can be done from small probes for a very long time now. So this is the decision path. So I've talked a bit about this, so I can go through it relatively quickly. As I hope I've convinced you, we needed to not rely on the Jupiter gravity assist. So we decided that we were going to provide direct to Neptune opportunities. That led us to having the SLS Block 2, but we could have also had the Falcon Heavy expendable with a kick stage in order to get us down to a cruise phase. Oh, this is important. A cruise phase plus main mission. So the cruise phase is 16 years. The main mission is 4 years in orbit at Neptune. So that whole thing is 20 years. And that was, we got an agreement from NASA that we could assume a lifetime of the instruments of 20 years based on the extra lifetime that missions such as Cassini have shown most of the instruments are capable of sustaining. Because if you go from the textbook, then you're only allowed to assume a full mission lifetime of 16 years. So that would have been a 12-year cruise phase, which is fine as long as we did the Jupiter gravity assist, plus a 4-year tour. So if you look at the options from the JPL study, Mark Hofstadter led, I believe that their main tour at Neptune was only 2 years because they had to consider the lifetime of the instruments. So that was something that we got the latitude from NASA to consider. So it's one of our risks is, can the instruments really live that long? I hope it's not something that we'd be required to prove in order for this mission to be launched. And that was kind of the agreement we had with NASA, was that we could assume that our instruments would last for 20 years. So once we had that, then we were good. We could choose our 16-year cruise, our SLS Block 2 in the kick stage, and we still get a 4-year, proper flagship-worthy 4-year cruise tour once we get to Neptune. We can also pivot to do chemical with a Jupiter flyby, so that's the enabled option. And then we recommend for future study the non-SLS, so basically the Falcon Heavy expendable. This is so I looked at a lot of these charts during the preparation of this proposal. So this is a really powerful way of displaying it, and one of our APL trajectory engineers, Marty Ozimek, was I don't know if he's the one who came up with the idea of displaying it this way, but he was certainly the one that I was receiving these from. So what you see here is the mass delivered to Neptune orbit, and then as a function of launch year, and then the time of flight is in the color-coded blue to pink. The crosses are the options with Earth, Jupiter, Neptune, and SLS Block 2, and in that case, you don't even need the Centaur upper stage. So even without the Centaur upper stage, you can easily get the same amount of mass. Here's our point design. So our point design was something a bit less, it's kind of this, it's ever so slightly, you can see it's the worst case scenario, it's the least mass, even though they're all kind of the same. But it's by a little way, it's the least mass that's delivered for any of the years after the Jupiter gravity assist goes away. So you can see we've got several launch opportunities in 2030, 2031, even 2032. Then once the Jupiter gravity assist option goes away, the first direct to Neptune only is 2033. So we chose that as our point design, and we delivered, the mass was just over 3.5, so 3,500 kilograms of our final mass. So the dots are where you have all of the launch options in that year that go direct to Neptune. So the power of this is you've got that launch opportunity available to you every single year. Although, we'd rather go sooner than later. But this is just showing you the approach orbit. The probe separates from the spacecraft ahead of the insertion burn, so that's slightly different to the Cassini-Huygens, where Cassini did its 90-minute burn, and then it dropped Huygens about 6 months later. And if you remember the palaver with it, it was supposed to drop Huygens a lot sooner, but it didn't, because there'd been a miscalculation in the Doppler shift as the probe fell away from the spacecraft. So always check your numbers. So this is in this case, our probe is deployed prior to the insertion orbit burn. So that is going to make for a little bit of a toe curling insertion burn, and also makes for, it's doable, but there's only 10 minutes between loss of communication from the probe and the insertion burn starting. So a lot of operations, a lot of the concept of operations to make sure that you get the data onto the spacecraft safely. We're probably not going to telemeter it down to the Earth until after the insertion burn. So you lose it if you don't make the burn, but that's space exploration for you. Here's an example of our tour at Neptune. So it's split into the phases that I described earlier. So we have the capture orbit in grey. The red phase is where we're doing the Triton flybys. We get a total of 21 Triton flybys during the whole tour. Then we do what do they call it? A crank over the top maneuver, I think, is to get us into the high latitude orbits. I must get a version of this where I have it in a different coordinate frame. So you can see when we get into the fast short orbits of the pink orbits at the end, it's actually going over the pole of Neptune and inside, hopefully, the radiation belts and the rings, and not actually hitting anything. But fingers crossed. So this is the unfortunate situation I was alluding to earlier when it comes to the power. So this is a plot that was shown by June Zakrajek at OPAG meeting, and she's recently shown this again, I think, in Stellar Probe, a solar mission, or a heliophysics mission, is faced with the same restore for plutonium situation. So what this is showing is based on an assumption of the current rate of production. So we just started making plutonium again in this country. At the current production rates, assuming which they could make it faster if they wanted to, and they have alluded to doing that. But at the current production rates, assuming we don't run over and nick the rest of the plutonium from Russia or suddenly find any down the back of the sofa, this is the amount of plutonium in terms of fuel clads for the RTGs available to us for the next decade or so. So you see that Mars 2020 is already earmarked one RTG. So this is yellow is the total available fuel clads with 2 MMRTGs for assuming for the next discovery. So we've got Dragonfly is already using 1 RTG. Mars 2020 is using an RTG. If the Triton discovery mission, which is a mission to Neptune to fly past Triton, we love it. If that is selected above all of the other discovery missions, then it basically means we can't do our mission because it takes 2 MMRTGs or next-gen RTGs. It takes the amount of fuel clads for 2 RTGs. And so if that mission is selected, we're in negative equity of plutonium and we won't have enough for the Neptune mission. The reason it was so important for Neptune to keep in, and we need just a sliver less than 3 full RTGs, and you can have partial RTGs. If that mission isn't selected, and of course we want it to be selected, it's such a schizophrenic feeling. But you want it because you want us to be going to Neptune, but you don't want it because you want to go to Neptune and you want to stop when you get there. Because Triton's a flyby mission. If that is selected, then there won't be enough plutonium to have a Neptune flagship. There we are. And I've also talked quite a bit about the opportunities for cross-divisional exploration as part of this mission. And I really do think that that's it should be the win theme of any of the missions that we're doing. And I think that's the importance of that is lost all too often. But a mission such as this, especially if we can persuade them not to hibernate during the cruise phase, should offer enormous opportunities for heliophysics, astrophysics, and additional planetary physics. I mean, we should target something in the asteroid belt, perhaps a Centaur flyby, which I don't think we've ever done. And we did have an exoplanets in our backyard, which is the title of a white paper I wrote for the Astrophysics Decadal survey. That's right. So I must see if they reference that. And then we had a workshop associated with that back in the before times. We actually got together in person in Houston, and that was terrific. And really nice to get all the astrophysicists and the planetary community in the same room and realize quite how completely differently we talk about things, which is really interesting. Here's the fact sheet for the mission. So this is the cost at launch, $3.5 billion. The power, basically saying we need the 3 next-gen RTGs, and the wet mass at launch. That may be a bit low, but on the order of 3,500 kilograms. And this is shown with the SLS Centaur at the stage. And I had another version of this where I put another Aurora on the side whimsically to say, it's not like your regular planets, but then I took it off because I thought it was a bit too sci-fi. So this was the team. We had a happy hour during our inevitable remote team meetings. And this is the tagline because we have so many scientists from so many different fields. It's Neptune, Triton, a flagship for everyone. And this is a beautiful, beautiful image of Neptune just to finish up. And that's what I had. And I hope that was of some interest to you.
Thank you, Abigail. That was great. We have a few minutes for questions and answers. Anybody want to ask anything? Raise your hand or just speak up.
Abigail, does Neptune have lightning in its clouds?
Very probably, but we don't know. And actually, we're just making a movie where I said, can you make it look like it's either aurora or lightning, just so that we can argue about whether it's accurate or not? It very probably does. We thought that it was going to be a lot more common at Saturn. It's quite common at Jupiter. We thought it'd be a lot more common at Saturn, but we've been there for several years before we made any observations of lightning at Saturn. I will go out and I'll put my neck out a little bit and I think it would be more common at Neptune because the friction between the neutrals and the plasma in the upper atmosphere is going to be a lot stronger, because they're going to be trying to be normal, and then the minute they become ionized, they're going to be trying to move to follow that magnetic field. So at Saturn, it kind of makes so that's where, if you think that it's relatively common at Jupiter, where the magnetic field and the spin axis are offset by 10 degrees, it's relatively uncommon at Saturn, where the geographic spin axis and the magnetic axis are almost perfectly aligned. So when you get to a planet where the magnetic axis and the geographical spin axis are completely off kilter, like 40 odd degrees, then you've got, wherever you've got fresh ionization, which is very much in that ionospheric, lightning, lower atmosphere boundary, where you've got plasma and neutral physics acting together, the minute anything becomes ionized, it's going to be trying to make what would you call it? A swan dive. It's going to be like desperate to align itself with the magnetic field, which is going to be in completely the different direction to where the neutrals have been going. So yeah, but we've never seen it.
Thanks.
Okay, thank you. Other questions? Everybody's so quiet today. We started off, everyone was talking. Now we're everyone quiet. Okay, well, I'd like to remind the students doing this as a class for credit that they have to do a oral examination with me next week. So we could do that by Zoom at whatever convenience you have available. And this is the last seminar of this semester, so we will resume physics seminars in February, I guess, since we're having a delayed start to our spring semester due to COVID. And we'll post that schedule as we start to accumulate. I have about 6 talks lined up so far. But if anyone knows other talks or speakers they want to suggest or have me contact, drop me an email and I'll definitely reach out to your suggested person.
I could give you, can I suggest a homework for the students then?
Sure, go ahead.
It's for course credits. We started a Spotify. We have, I should have put the link in my presentation, but we have a Spotify account for Neptune, where people were suggesting songs for the theme songs that would be fitting for this mission. So I think that's something that I like the younger generation to play, to help us out with, so that we don't have it all be folk songs and David Bowie.
Okay, well, you heard the assignment. See if you could come up with a theme song for a Neptune-oriented. I believe Vivaldi had a Neptune's, what was part of his planets, right?
Go on, that is highbrow. All right, I'll take that. That's a good.
Okay, everyone. Thanks a lot again, Abigail, and thanks everyone for attending.
It's been a pleasure. Thanks, everyone. You all take care out there. Just get in touch
Thank you very much.
if you have any questions, or if you anything at all, just drop us a line.